Hi, we're here at Lift in Detroit, and we're here with John Keogh, who's going to tell us a little bit about what Lift does. And with Scott Johnston here, he's Lumafield. He can tell us why Lumafield fits so well into Lift's structure here, and we'll hear all about the rest of the details.
Perfect. Awesome. Thanks, Tom. So welcome to Lift. Lift is a 501c3 nonprofit manufacturing innovation institute. There are roughly 17 of these MIIs in the country. Each have their own swim lane or focus. Some focus on renewable energy or flexible hybrid electronics. Lift, we focus on advanced materials, manufacturing processes, and systems engineering for extreme environment applications often, but not exclusively, amid a whole range of other applications as well. So we'll take you on a quick hot lap tour through the facility. We'll stop at Lumafield and talk about why we're partnering with Lumafield and why the fit's just right. And then we'll kind of continue around, and then we'll actually land in another Lumafield system and kind of bring it home. So right here, we call this kind of members row, if you will. So you can see we have the North American Die Casting Association. We actually have Kearney here as well, previously A.T. Kearney, so management consulting firm in the world of manufacturing and technology. And then we also have Siemens as well. Siemens has quite a heavy presence. And then, right center stage, we have the newly minted Lumafield cell, right? So I mentioned that, at Lift, we focus on developing advanced materials and advanced processes in a lot of respects for national security, for national defense, things like that. When you're dealing with new materials or new manufacturing processes, you need to often look inside of them. If you're joining things, if you're welding them, if you're making a new thing, you really need to understand what the internal structure of it looks like. And that's where CT scanning comes into play, right? So it's a key enabler. And historically, up until meeting with Lumafield here, the world of CT has been quite a challenge. It's very expensive. Systems themselves are incredibly expensive, and they come with a lot of risk. CT is an X-ray technique, right? So you have an X-ray source, you have a detector. If the source fails on a system that you own, that could be $50,000, $60,000. If the detector fails on a system that you own, it could also be $50,000, $60,000. The software for reconstruction and analysis also is incredibly expensive, anywhere from, again, $50,000 to maybe $90,000 per license. Lumafield has taken that risk away from the customer, right? They've simplified the approach. So now with the model that they approach in advance to their customers, you don't have the risk for equipment failure. The software is far easier to use than most traditional CT software. It's cloud-based. There's just kind of an endless realm of benefits to working with Lumafield. So we at Lift really, really like what they're doing. I like to say they're democratizing CT scanning, right? And that's kind of our charter at Lift really as well, is to help democratize the tenets or opportunities of advanced manufacturing and analysis broadly to the industrial base. So that's why the fit with Lumafield and Lift is just right, and it's key to us. So did I hit the nail on the head there?
Absolutely. Yeah, our presence here at Lift really fits with our vision of not just democratizing X-ray CT scanning, which has traditionally been kind of a specialist's tool for inspection, but also it fits with our broader vision of taking X-ray CT and turning it into a general purpose tool for manufacturing inspection. It fits with this plan that what we think of as software-defined inspection, right?
Yep.
The idea that in manufacturing inspection, you might test for failure mode A or failure mode B, and you use 12 different pieces of specialized test equipment. With X-ray CT, we can get one volumetric image that becomes a digital twin of the thing you've made, and all of your tests on that become lines of software that we can run arbitrarily on that model. So we believe this is really the future of manufacturing, and we're excited to be here along with all these other partners.
Yeah, and we're excited to have you guys, absolutely. And again, the opportunity for this type of analysis in the setting of manufacturing helps to manage quality, helps to manage throughput, right? And helps us to get as a nation to the solution of building things faster, better, cheaper, first-time quality, that type of stuff, right? Trying to really regain competitiveness on a global platform where, historically we've kind of lost focus on it. Now we really need to figure out really how do we step forward as a nation and regain competitiveness on the, the global stage, right? So
Now we're here in the Lumafield stall, if you will, here to understand better what they do. And we're here with Scott Johnston to tell us the whole story.
Hi. Thanks. This is our LumaField Neptune CT scanner. This is the world's most accessible CT scanner. It is first and foremost an X-ray machine. If I open the door and look inside, you will see that over here there is an X-ray source on the right. It sends out X-ray energy in the form of X-ray photons through the sample. I've thrown a PCBA in here to look at. And that energy hits this carbon fiber plate behind which is our X-ray detector. We chose carbon fiber because it's transparent to X-rays, or has very, very low density. We've designed this machine to be easy to use, to be accessible, to fit into any office, laboratory, factory space. It fits through a standard doorway. It plugs into a standard outlet. It's priced very aggressively, and part of the way we can do that is by offloading the computing to the cloud. So when you take an image on this system, you'll see right away a 2D X-ray image forming of the board that we've put in here. When you run a CT scan, you're able to get a third dimension out of this image, and it maybe 2D for some applications 2D is enough to answer the question, but it doesn't give you the depth, right? So what happens is the part is sitting on a turntable that rotates while we're scanning. We'll take hundreds or maybe thousands of 2D X-ray images. In a hospital CT scanner, which you may be familiar with, the X-ray source and detector rotate around the patient. Here in an industrial CT scanner, the X-ray source and detector are stationary and the part rotates inside of that beamline. So same action, but in this case, these images get uploaded to our cloud service where they're reconstructed into a 3D volume. And what's really cool, something that's really cool that's happened in the last few years is the falling cost of GPU computing in the cloud has allowed us to do that reconstruction in a very cost-effective way. Just a few years ago, if you wanted to do X-ray CT scanning in your lab, you would need a very high-power workstation with 4 graphics cards and hundreds of gigabytes, if not more, of RAM. These data sets are huge, and they're very difficult to work with on a workstation. And even just copying those files has a lot of friction. If you're talking about trying to share 5 or 10 gigabytes of data at a time, that really adds up.
And that's probably just a small part size.
Exactly. And so with LumaField, right, yeah, we're doing all this in the cloud, so you don't have to deal with that. You hit the automatic scan button, and it starts going. And when the data is reconstructed, that volume lives in the cloud, and then we can serve it up to you in your web browser very quickly. And you can view that on any laptop or desktop, or even a mobile device like your phone. I saw you looking at the scans on your phone earlier.
Very impressive.
So also because it's cloud-based, we have a lot of collaboration features. So you can share scans as if in a way that's very similar to a Google Doc. So a lot of powerful stuff you can do.
So some headline figures here: electron volts, resolution, maximum part size.
Yeah, good question. We actually offer the system in 3 different X-ray configurations currently, depending on the types of materials that you're trying to scan. The particular machine that we're looking at here has a 120 kV X-ray source in it, and that is really optimized for scanning plastics and polymer materials and electronics. We have also a higher power system at 190 kV that we use to look through denser metals, and we have a lot of customers actually scanning individual components as well as assemblies. So a lot of people working on plastics with this machine, a lot of people working on various types of metallic assemblies with our high power machine. And we also have a microfocus version of this product, which has a 130 kV X-ray source, but it also has a very, very small spot size. And the way this works, it's similar to optical imaging, where if you have a very, very small spot, you get a very crisp image that you can magnify. The way we're able to image very small things is through magnification. It works just like optical light.
And how small are those points?
We can look at, with the microfocus system, we can resolve details down into the 6 micron roughly kind of size. So really, really crisp and clear enough that you can look at very fine details on a PCB, which is something we'd like to take a look at today.
So for comparative reasons, how would this compare in specification to, say, the CT scan that's now at our airports scanning our luggage? I mean, the output looks very similar, but it's a much bigger machine, and it does do what you said, where it surrounds the object being scanned, and much like a medical one. But
we're We're optimized around very different operating points. Here, our goal is to extract as much information at the highest resolution possible. In an airport, they're concerned about throughput. So those scanners tend to operate at a lower kV and higher current. They can make images very, very quickly, but their resolution is more similar to a medical CT scanner where you're looking for millimeter size objects. So our customers are primarily in engineering and manufacturing, and they're really looking for microns. They're looking for, do I have porosity in my injection molded plastic or my die cast aluminum? Do I have the right compression on my gaskets in my assembly? Do I have a fit issue with my circuit board? Do I have tears in the separators inside my batteries? And you need to resolve microns in order to see those kinds of things.
You have some other parts that you can show us here, I think, if I'm not mistaken.
Yeah, I'd love to show you some of our scans.
And in fact, this one is of particular interest to me personally. This is a Danfoss power module. And inside it, it has sintered connections to make the connection to the heat sink and other terminal connections. And I would love to see what that looks like on the inside.
Okay, here's that power module that we scanned for you from the Rivian R1T. Right away, we're looking here at a view of the 3D model. I want to show you the data that we get in the form of radiographs. So these are, like I was saying, when we do a scan, we're collecting a sequence of 2D X-ray images. And here you can see what that source material looks like. This is the sequence of 2D images that come in, and I can kind of scrub through it, and you can see the rotation of that part. In this case, you can see also the way we've fixtured it inside the machine to a piece of carbon fiber here. So it rotates around, and we're able to capture the detail at all these different angles. And what the reconstruction process is really sorting out is, what is the 3D volume that could have produced this set of shadows? It's a really interesting way to think about it. But anyway, with that, we're able to produce this 3D solid. And what's really cool about the 3D model is that you can manipulate it as if it were CAD. You can fly through it. You can slice it arbitrarily in any plane. You can take dimensional measurements on it. You can compare it against a CAD model, and we can give you a heat map that shows you where dimensions deviate. In this case, because we're doing reverse engineering, we're just going to kind of slice and dice and look inside and see what we can see about this. So here are some slice planes that we've set up that are parallel to the plane of the device. Here you can see the metallic inner layers here. I believe this is a silicon carbide MOSFET, if I'm not mistaken. Yeah, and you can see the isolated pads in here. You can see the bond wires, of which there are many, connecting the different layers. And yeah, and some interesting notching on that copper. I was trying to map it out to the features, the tabs that come out externally here. I'm not sure the purpose of some of these notches, but I'm sort of puzzling over that. One of the things that happens to your brain once you have X-ray CT is that you start wondering about all these little hidden details in other people's designs. And then as we scrub through the plane here, you'll see these really cool raised, I assume this is copper or brass coming here for the...
That's a very good question.
Yeah, but this is cool. I actually never seen a power device with an integrated liquid heatsink interface on it before.
Well, but the idea is that it creates a sort of tortuous path for the coolant to flow over the top of it, and it takes the heat away accordingly. It's a way of creating a very effective heat coupling without a corresponding large pressure drop across it for the pump to have to drive through and such. And
I saw your video. It looks like there's a slot here and a slot here and some gaskets in the way this is mounted. So yeah, really, really fascinating design. So we can kind of scrub through here and see the connectivity, the internal connectivity of some of these other layers. And so if you really wanted to study this and map out the way this is bonded out, you can really...
The image looks well aligned to the plane, if you will. Is that something that you had to manually line up, or does the software do that for you?
A little bit of both. We can do it manually, but we also have some tools to automatically align things, especially on parts that have some obvious planar surfaces. We can orient them, and then you have some coordinate systems set up around that you can play with. Another powerful tool is that X-ray CT has. Because it's 3D, we're able to look at pores and voids, you can see here that nothing is perfect. There are little glitches in the the inner layers here. I'm not sure what the construction of these is. You know, as I'm clicking through here, I'm clicking on bookmarks that we've made. This is a really nice feature of our Voyager software. I think, you know, Voyager runs in your web browser. This is like a very unusual thing in X-Ray CT, that you can just click on a link and, you know, browse through this you know, so easily. But this is ultimately, these bookmarks are the thing that you can share with your colleagues. You can add comments and tag things. So you can have kind of a dialogue about specific views of a part.
So what if I wanted to say focus on one of these welded joints there where a bond wire connects to a terminal?
Yeah. So you know, two things. You know, first of all, we can zoom right in here and you know, look at it directly. We can also create what's called a region of interest, which is basically defining a box around that area. And I'll show you some examples of where we've done that. This is the overall component that we've scanned, and these boxes that you see here tagged ROI1 and ROI3, for example, are subvolumes. And what's happening here is that in order to serve these volumetric solids very quickly to your browser, we've downsampled the data from the, like I was saying, it's many, many gigabytes of data stored in the cloud.
We down it somewhere.
Exactly. We downsample that to send it to your browser. So if you really want to get in and extract more of the original detail that's present from the scan, you can create these regions of interest, and the server will resample the data and serve you just that volume. And so I can click through, for example, on ROI1 here, and you know, now we're able to look at just that section that was in much greater detail than we were able to see before. And you know, I can play around over here with, this is what we call the range mapper. It's sort of like a histogram in an image editing tool, but unlike, you know, an image, what you're seeing here are peaks of density of different materials. So we can open and close these barn doors to apply our color map, which is you know, sort of a false color map, but it corresponds to density. We can apply it over any range of actual X-ray material densities. So you can, for example, exclude plastics or to focus on metals, or try to exclude metals and look at plastics. In this case, we're scanning a part that's very dense already, so it's a little bit more challenging to extract some of those details of the lower density materials, but you'll see in some other scans we can do that very successfully.
So now you asked the question, is this copper that's plated? I would imagine with enough detail we could see that there is a plating on it.
Yeah, possibly.
Maybe not with the scan you've done.
Yes. Yeah. With very, very dense materials and very small thicknesses such as platings, it's pretty challenging to resolve, you know, that level of detail in a typical scan. But there are ways we can try to look at it to extract that information.
For data size management, these ROIs, I assume you could focus solely on the ROI in the scan and minimize how big the data is when you're done. Yep. And maximize the resolution of a particular area you're focusing on.
Yeah.
So very interesting that we can get that sort of detail and fit it on a hard drive of any type. And it's nice that it's on the cloud, so that it's also backed up there.
That's right. Yeah. And, we found that for traditional CT scanning, data management is a serious pain point. You wind up with racks and racks of hard drives and random hard drives and USB sticks in desk drawers, and just being able to recall a scan is a big proposition for a lot of people. Here you can just email someone a link.
So what about scale? We've seen two machines. They appear to be roughly the same size. Are you looking at bigger machines?
Yeah, you know, we have a lot of other stuff in the pipeline that we're actively developing. You know, right now, you know, we can scan objects about the size of a basketball and a little bit larger with some different scan techniques. But yeah, we're always looking for where we can make the most impact in the market. Right now, we're focusing very heavily on you know, this machine here was targeted at the R&D and NPI kind of workflows. We are focusing right now on you know, high volume CT scanning. So we're investing a lot right now in automating the kinds of analyses that we're doing here manually and visually, and you know, adding automation to allow you to scan hundreds or thousands of parts in a 24/7 lights out environment.
So it's going to be a while before I can put a whole vehicle in there and scan it. I'm going to need a few more electron volts too.
Yeah, hang in there. It might be possible.
And do we have enough hard drive space on the planet for that one?
That's right.
I'm not sure.
Exactly. Exactly. Yeah.
So that being the case, it does give me some curiosity around being able to turn these 2D images into multiple 3D images. For example, how wonderful would it be that I could characterize an individual bond wire and have a 3D model of that? Are we getting to that point, or?
Yeah, can I show you? Maybe a good example would be to look at the PCB that you brought, and
Wonderful.
we can look at that and see what we can do with that data.
Okay, sounds good.
All right, this is the Tesla board that you guys loaned us. Can you tell me a little bit more about this?
I believe that is a high-end processing board that takes camera signals, if I'm not mistaken. I wasn't part of that particular teardown, so I can only speculate.
Yeah, it's one of the densest boards I've ever held.
It is.
It weighs almost a pound. It's like solid copper.
And when's the last time you saw that sort of density in an automotive application?
Exactly. It's a very impressive
satellite
layout.
or at least aerospace level density.
Exactly. Yeah, I was enjoying all the fun labels on here too. There's even a selfie cam connector labeled here. But so this is the CT scan from this board. We ran this for you, and this is the complete circuit board here. And we can dive in and take a look around. And even slice through this board and visualize kind of the different layers of the board. We've set up some slice planes that are parallel to the board. But actually, looking at this in greater detail, I want to take you to a section view of the board. This is another fun thing we can do with X-ray CT scanning is kind of zoom in and capture a section of the volume in higher detail. So we ran this on our Micro Focus system in here. And so this is a detail of around one of these processors. And as you can see, there are these cool like stiffening spiders on the back that straddle a lot of capacitors. There's memory right up around the sides of these things. And it's really just so impressive to me as somebody who's done a lot of PCB layout to look at this in 3 dimensions and kind of marvel at the stack up of components that's involved, particularly around this part, this very dense BGA. Not only is it surrounded by capacitors, but let me see if I can get in here and get you another view of this thing. But I can kind of spin this around in 3D and show you just how impressive it is that there's actually capacitors inside of these BGAs as well. There's some kind of multi-chip module happening here. So. I can scrub through layer by layer and show you some of that if you'd like.
Sure. While you're doing that, I'll kind of explain what a BGA is. A ball grid array is a series of little tiny balls that connect together and they get melted together, and it becomes very difficult to know, particularly on the inside, whether or not there's been a good electrical connection. So it's been standard fare in the BGA business for years to do X-ray inspection of these things to make sure that you've got your thermal profiles correct for the assembly of the circuit board. And here's a great way to inspect it and make sure that it's been done correctly.
Yeah, our customers ask us about BGAs a lot, so something I hear about frequently. When you look at something with this kind of density, it is kind of a wonder of, process control that you're able to reliably solder something like this with all these different, thermal masses in place and all that. So, here we are, we've defined a plane that we can kind of virtually section through, again, parallel to the board and look at that BGA. Here, I'm gonna scrub through down to, these are the layers below the BGA. You can see this, this metal stiffener here that surrounds it. I assume that probably is there to back up the heatsink that's applied over the top of this thing. I saw there were some traces of thermal compound left behind here. But then if I scrub the other direction up through that ball grid array and up into the chip itself, you can see something really cool emerge. You can see the structure of the chip under the lid here. And this is something that previously you would need to get really bold and pry the lid off and get your microscope out to see. But here you can see under the lid of that chip, inside the chip itself, are a lot more capacitors, and you can see the chip itself that's in here. I can't tell because of the cropping whether there are multiple dies in here perhaps, or what they've tried to do, but it's a really interesting way to see how people are approaching integration. I'd like to show you perhaps I can show you. Well, here are the balls on this particular BGA. Actually, we can resolve them in really great detail, and as we scrub around, you can help. One of the challenges with BGA soldering is porosity, and porosity is kind of or voiding, as they would call it more likely in the solder industry. Anytime you have a material process with a phase change happening, solid liquid to solid, solid to liquid, you introduce the possibility of gas bubbles, and that certainly happens in soldering. These are kind of the bane of the process engineer's existence. With X-ray CT, we can identify exactly where they are and how large they are. You can't avoid them completely, but we can certainly quantify them and say which ones are out of spec, right? And
so that we are seeing some evidence of that in these small.
Exactly. And it would be very difficult, given the density of this board, to resolve that in a 2D X-ray. So this is one of these applications where, although this is a 2D image we're looking at, it's a slice of a 3D volume, and we can manipulate the plane in which we're viewing it. So here I'm just scrubbing up and down through those balls under the BGA. But I can show you on a scan we've done of another circuit board, that's a little bit less dense, can show you some additional insights we can draw from that if you'd like. So here's another scan we've done of a circuit board. This is, I believe, a microcontroller eval board. So here you can see another ball grid array in the middle, but now because the board is a little bit less dense with copper and features and components, we're able to really resolve in exquisite detail the different layers of the PCB. We're able to resolve the via structure. We're going to be able to show you, you can even see the plating between the top and inner and outer, layers of these vias. And you can basically, very easily reverse engineer this entire circuit from the CT scan. But one of the things that just never gets old to me is looking at this scan, looking at slices through the ball grid array. So again, I've done the same thing that we did on the Tesla board here, where we can kind of scrub around and show you the porosity. And here we can actually automatically identify it. We have a porosity detection feature that you can set up some thresholds around and color code the pores by size or distance to the surface or any other metrics that you're interested in. So here you can see kind of the distribution of pore size in this particular data set we're looking at. We can kind of play around with that and visualize a lot of different things. Here, I mean, this is the power of 3D talking, but here is just a subset, a region of interest that we took of the balls under that ball grid array, where we're able to look at them in 3D and forget about pore size. Now you can just visually understand what's happening with the gas bubbles that have formed here. And this is 3D, and I can manipulate it as if it were CAD and fly through here and zoom in and all of that. And this is just, I don't know, this is just really super cool. You talked about colors. We can actually play around with the colors to kind of exaggerate different things that we're looking for. So in some of the images I've shown you, they've been a black and white color map. Here we've used the rainbow color map to kind of accentuate some of the density differences in this image that we're looking at of another chip on the board here. So another thing that is pretty cool, this is actually a cross-sectional view of an inductor on the board here. So you can even look at an individual component with a pretty high level of detail and understand, if I wanted to play around with this, you can understand, is there a break in that wire? How is it routed? Are the windings even? So you can
at scale, I can tell what gauge that
exactly,
is.
Exactly. You can just dive deeper and deeper and see things that you weren't even looking for. And that's something we hear very consistently from people using our system, is that they come in looking for problem A, and by the time they have left, they know about 6 other things that they weren't looking for as well.
Not all of which were welcome, I'm sure.
That's right.
All right, good stuff.
Yeah.
So in summary here, this is a new way forward for everybody. It has implications for us at Monroe & Associates. As we tear things down, we don't have to take things apart as much anymore.
Right.
Like I said, my only regret is that it doesn't do much larger systems. I have a battery right now I'd love to put inside one of these things.
Yeah.
Make it a whole lot easier to know where to probe when I'm taking it apart.
That's right. Would you like to take a look at a battery?
Sure. Let's see what a cell looks like.
Yeah.
All right. Very nice. We can see the individual layers of cathode and anode and separator.
Yeah. Can we back up a minute? Can you tell me, this is a battery cell that you sent us to scan. Can you tell us where this came from?
I cannot. I do not
Okay.
have any knowledge.
It
of
was
that.
labeled Hyundai Ioniq 5.
Oh, well, I can tell you where that came from. Yes, we
Suppose-
were a part of an Ioniq 5.
Yeah.
And we extracted the battery cell, so we gave you one, and this one is a pouch cell. So that means it's somewhat flexible in its shape and appearance. It's got a plastic envelope that it all sits inside. You can see the edges of the envelope out in the perimeter of the scan here. And you can see the individual layers of cathode and anode that are distributed throughout the array internal to the cell. It is a common scheme to cool these cells by their edge. So it's important to know that for the alternating layers of copper and aluminum that these lines represent, it also is a path to extract heat out through that edge.
I didn't realize that. That's really cool. Here we've got kind of some section views of that cell. So we're able to see some interesting stuff. Again, given the size of this battery, we really just scanned the corner to try to extract maximum detail. But can you help us understand kind of what some of these different layers are inside the cell?
Sure. So every lithium-ion battery, most batteries in general, they're all constructed very similarly. There's a layer of copper that has energetic material on it. There is a separator. There is a layer of aluminum with energetic material on it, and that's all bathed in an electrolyte. So it's probably not going to be obvious where there's electrolyte as a liquid in this image, but the hard parts are certainly evident. And the various layers of separator are quite different in density than the copper and aluminum layers are. And I would imagine if we dug deep enough into the resolution here, we could see the coatings that are on the different foils of aluminum and copper that would constitute the anode and cathode materials that we always talk about.
Yeah.
So this looks like a welded tab connection at that.
Yes.
So if we were to dive deep into this, we would be able to tell that there is a weld, and how good of a quality of a weld that is. That would be an important attribute of any sort of battery assembly.
Yeah. These connections are really interesting to me because the material seems so fragile. It seems like it's really difficult to connect them together without tearing them or disturbing them.
Well, it is one of the downsides of the pouch cell, is it's a relatively frail device when you're done. It's very easy when you're extracting them out of a battery pack to breach the envelope and have some bad things happen in your laboratory environment.
Yeah.
You certainly don't want the envelope to open up and the electrolyte to come out and or the fumes thereof.
Yeah.
Certainly not anything you want to breathe or touch.
Yeah, absolutely. Now there's kind of a 2D view of that happening there.
All right, so we've finished up our session here at Lumafield and come away with a tremendous education on what the view of the future is all about. It'll be a whole lot less laborious to tear things apart if you can do it in the virtual world. Baby steps. We'll get big enough eventually where I can bring a car in. I'll probably do all pretty well with that until I try to drive the car away afterwards. That's
Right.
not a good plan. So that's probably worth mentioning, is that this is a somewhat destructive process. So you don't
For
want to
very, very long doses. of
Right,
X-ray
right,
energy.
right.
For
So-
electronics specifically.
for electronics specifically.
Yeah.
But again, that's not the use case. You're not
Right, exactly.
inspecting every part. You're inspecting
Exactly. For the most
periodically.
part, it's non-destructive testing.
So again, we've had a great journey here. We've seen their machine. We understand where they're going with it. There's different sizes, different applications, and it's all exciting.
If you guys want, well, I guess we'll continue and maybe do a hot lap around the facility to see where, some of the rest of the things that are happening here that actually help, make the setting make sense as to why, we're partnering together. So right here, you'll see this is incremental sheet forming. Basically, it's a robotic application that allows you to make parts that normally would require, expensive tooling, stamping presses, things like that. It's great for prototyping or orphan or obsolete parts. It's definitely something that's of keen interest. And again, if you want to understand if this process is inducing, say, cracking in your parts, things like that, you would go ahead and toss it in a CT scanner and actually start, running the analysis and looking for indications of quality, right? So we'll keep on going this way here. So this is our digital twin. It's basically a smart factory trainer for our education workforce development side of things. Basically, the idea is that this is a cell in which students can engage in, say, robotic programming, PLCs and integration, detection, online controls, and so on and so forth. So really, this is kind of an extension of our learning lab that's elsewhere in the facility. Siemens has a very large installation here. So the way I like to say that this is a immersive environment meant to show what Siemens can do from a hardware and software perspective, cybersecurity, and so on. And it's a story that's told in the setting of autonomous vehicles and electrification, right? So there's also AR trainers, so augmented reality. There's cobots and AGVs, so automated guided vehicles, etc. So coming back this way, there's a lot to talk about, but I think we can only cover so much. This is an example of what we call a directed project that we ran with Ricardo Defense. Basically, the initial project was to outfit Humvees with electronic stability control systems and anti-rollover systems as well, because you can imagine as you put more and more stuff on top of these, they get, the center of mass goes higher. And unfortunately, we lose, at least 20 soldiers per year to rollover accidents. So this was a wildly successful program, reducing rollovers by 74%. That's actually mapped into a $90 million follow-on, and now I think roughly an $800 million follow-on project as well. So definitely important work here. We'll come this way here. So I mentioned that LIFT as a National Manufacturing Innovation Institute, we focus on developing advanced materials, manufacturing processes, and so on. We leverage the digital environment, so modeling and simulation, or integrated computational materials engineering, to a very deep extent, right? Trying to run the experiment in the digital space first. And once you get to either a set of materials or chemistries or results that you actually want to prove out, you need to be able to do the thing, right? You need to actually be able to make material, make something with the material, test its properties and performance. And so that's kind of what you see in this setting here of LIFT. So we're really standing up the capability to produce custom metal alloys in development volumes, so say 30, 60, 90 liter batch volumes, and then turning them into feedstock where we can either make powder for powder additive processing or wire for wire-based additive manufacturing, so on and so forth, right? And then also leveraging the physical systems that are here then to make something with the material that we made, that we designed with the digital side of things, right? So you can see how that all kind of folds together. And all throughout that chain and the physical, inspection is critical to us, right? So again, being able to look inside of a part without having to chop it up into thousands of pieces offers immense value. In additive manufacturing, for instance, you're actually making the material as you're making the part. And as you go through that, there are going to be location-specific material properties and characteristics of the process. And being able to inspect that part throughout its volume on a location-specific basis and relate it back to the process log that happened, it offers a key enabler, a key value to really help elevate the processing and the additive manufacturing that we do and bring it into the forefront and into adoption. So we'll keep going this way here. So you can see this is our crane bay here. This is actually our shipping lane. Everything's in a state of flux right now as we stand up this custom alloy and feedstock production initiative. So you'll see some robots and staging over there and rails and things like that. So everything's always changing here. We're really quite busy all the time. Right here you see the world's largest tooling envelope linear friction welder. So this is a solid state joining technique. It means that you're not melting the metal. If your hands were metal and you were incredibly strong and rubbed them together, eventually they would become one. So we use this for a lot of aerospace and heavy equipment applications, very high value applications where you need very, very strong joints, if you will. Machine shop back here, over there. We also have some double action servo presses back there. We can use them for forging or for stamping or actually materials testing as well. So compression testing or formability testing, things like that. And then coming this way toward the west, we get into some of our education and workforce development initiatives. So we have our welding training center here where our students go through and they get an AWS certified certificate. They focus on MIG welding, TIG welding, plasma cutting, positional welding, so on and so forth. So we have a lot of students that come here either to learn a new skill or to upskill, right? And then they take that cert and they can bring it to the workforce to either, start a new career or, get higher pay, right? And this right here is actually our CNC operations training center. So doing the same thing. In this case, it's a NIMS certification, which is, the certification to have. So we have a CNC mill and a CNC lathe there. And if you pan right here and we can walk around and turn directly backward here, you'll see that we have another Lumafield system here. And it's deliberate. We're standing up, we're really building a relationship, right? A partnership with Lumafield. We do have other CT scanners, and the long-term plan is that everything that we have here as far as CT will be Lumafield. So I don't want to, let the cat out of the bag, but there are things in development at Lumafield that Lift is very, very interested in. And this system, coupled with some other things that are in development, will supplant everything else that we have here, and eventually will be exclusively a Lumafield CT system, organization. So again, 2 other CT systems here. They have their purpose, but again, democratization of CT is key and critical to us. There's some stuff here that's tarped over, so custom alloy, melting, casting. This whole area will be completely different in 6 months' time. Heat treat, vacuum induction, melting, you name it. These capabilities will allow Lift to produce custom alloy feedstocks across the entire metallic periodic table. Off to the right here is our Met Lab. It may be worth a quick run through. So as far as metallography, all your standard equipment plus more. So cut, mount, polish, etch, right? Light optical, scanning electron microscopy, of course a range of balances and imaging capability. A lot of capability for density measurements. We have Phil here. He's always busy in here. And then hardness testing, mechanical testing, of course, are standard fare. We also do some of our own electronics development here. So sometimes we need custom circuits. This here is our SEM system. And eventually here we're looking to upgrade this, but it's good enough for now, but we have some really specific needs that we're working toward to upgrade this system here. So 3D scanner here, so Keyence 3D scanner here. Light optical microscope here. We have a laser profilometer here. So we also have density measurement, another type, and then this is also a particle size and shape analysis system here. So we're making powders. We need to be able to characterize the powders and really, put some numbers to it. Coordinate measurement machine here. We have kind of your standard fare load frame for tensile testing, yield, elongation, compression, things like that. We have a Trillion digital image correlation system here. This is really critical actually because it allows us to do what we call optical strain mapping. So we can really get a strain field as things are deforming, and that tells you a lot about the material as it deforms and as you're pulling it. So then, range of a bunch of these little polymer printers. We use them all the time. X-ray diffraction here as well. So we love X-rays. Powder and single crystal. Bend testing for weld integrity. And then this system here, right here, is actually really interesting as well. So I think of this system and the Exum team in a lot of ways similar to Lumafield. So Lumafield's democratizing CT scanning. Exum is democratizing mass spectrometry. And specifically, really, this system is actually meant for elemental analysis of solid state samples, whether it be metals, ceramics, so on. It plugs into a 110 volt system. It effectively displaces the need for $1.5 million in equipment in ICP OES or ICP MS, which are other techniques which are meant to analyze the chemical composition of something. And you don't need a whole laboratory to support it. So my background's in mass spec actually, and really what they're doing here is transformational, and I hold them in the same category that I hold Lumafield as well. So it's I'm an instrument guy and by training. And this is the type of stuff, Lumafield and Exum, that warms my heart. So go this way. All right, and then we have some plasmatry systems here. That's for coating surfaces, for cleaning surfaces as well, in preparation for, say, joining by way of structural adhesives, or even just applying different types of barrier coatings. A pallet welder here that we can use for, say, wire arc additive manufacturing and so on. And then what is missing here is a completely different cell that is actually kind of in a retrofit right now. It's a robotic multi-wire plasma arc welding DED cell, so directed energy deposition. You can think of it as large format additive manufacturing with metal and a welder. But what we're doing is some really, really cool stuff here. So, and again, parts made here. We'll take pieces of them, scan them in the Lumafield system. Look where there's lacks of fusion, where there's porosity, things like that. So it's really, again, critical to be able to acquire that data. And then we have an extrusion press here. I sweep around to the left there. So, we've all seen extrusions and used them. May or may not know it, but it's basically a Play-Doh fun factory, right, with metal. So adding a lot of capability to that here. And then kind of landing at the end over here, we have this large press. This is a 1,000-ton press that can be operated as a mechanical press or a hydroformer if we want. Currently, right now, we're using this against a project where we are developing, proving out, and commissioning and running off a line to produce electrochemical separator plates for one of our government partners, and the rest of that will be over there. And you see some other construction as well there. Again, I mentioned earlier that we're really intent and heavy on the digital side of things. That room that's being built is our mission control, right? So with mission control, we will be taking all data streams from all equipment, feeding them to the central brain, if you will, and then any given manufacturing process, we can track those parameters and look for indications of quality during the manufacturing process, and B, also use machine learning algorithms to interrogate that data stream and then feed back process adjustments in real time to really help manage quality with short and long-term trims and make sure that what we're getting is the best part all the time. Again, getting us to the status of faster, better, cheaper. So kind of the overarching vision of everything we do is digital. There's a digital wrap around everything, and it's really meant to augment and support what we do in the physical and mitigate a lot of the empirical make and break effort that we've used to have to kind of endure and make things a little faster and a little better for us. So that is the nickel tour of the high bay. There's a lot more to say, and there's a whole lot more to say about LIFT, but really this is about Lumafield here. And we're thankful for your partnership. We're excited about it. It really, like I said, warms my heart, and I'm looking forward to the future. So,
well, I can say that Monroe and Associates is truly excited to be here as well. It's great to be on the cutting edge, partnering with companies like LIFT and Lumafield to stay on that cutting edge for our viewing audience at Monroe Live, as well as for our own internal engineering operations as we tear things down and wonder what's inside.
Yes, indeed, yes. Yeah, and we're thankful for you guys coming out as well, and we'd love to have further conversations.
All right,
so,
very good.
For sure.
Thanks for the tour.
Yes, Scott.
Appreciate it.
Thanks, John.
Thank you. I appreciate it, guys.